Now it is the time to perform logical synthesis using RTL compiler. So to invoke this RTL compiler, just provide the command rc followed by a switch GUI. So this would invoke two windows. One is the RC terminal window, the other one is the GUI window. During this synthesis process, there are basically 7 steps that are involved. The first one is to set some attributes, and the second one is to load the library and the RTL design, and third one is to elaborate the top module, and the fourth one is to apply the constraint, and the fifth one is perform synthesis, and the sixth and seventh is to generate the reports of area and timing as well as the synthesized netlist file. Now, as I stated before, I need to set some attributes. The first attribute that I'm going to set is for the HTL search path, and I'm going to specify to search in the current directory itself. So here the dot denotes the current directory. The second one is to set the search path for the library. So for that I need to give set attribute and then lib underscore search path, and I am telling the tool to look into the current working directory itself. Now once these two things are done, there is again an attribute for the information that the tool needs to provide. So this is set through the variable information underscore level, and the recommended level is of 6. Here the value can range from a minimum of 0 to a maximum of 9. So I'm just setting to the recommended level of 6. So any information that it provides like timing and area report, it's all depend on the number that I've given. So the greater the number we give, the greater the information that we can extract from the tool. So the next thing is to load the standard library cell. So this is again set through the command set attribute, and the variable name is library, and the library that I want to load here is std.lib.lib, and this library should be present in the current working directory that I have invoked the RC2. So this is the file that we have created in our liberate tool, and make sure that you have copied this particular file into the directory from where I have invoked my RC2. So when you click enter, it has certain warnings just because we have not defined any area definition for the cells that I have defined. And the next thing is to read the HTL file into the compiler. So for which I need to provide the command read HTL and the full adder .v as well as the half adder .v. Just click enter, and we have read both these files which are there from the current directory. Now I need to perform elaborate, which is the third step, by invoking the command elaborate, and then you need to specify the top module name which is available in the full adder.p. So the full adder has a module name as full underscore adder. I just give the same name as the top module name, and after this we just click enter. After I elaborate the design, you'll be able to see this GUI window right now shows us the full adder circuit. Now this is basically been constructed with half adder, two half adders, and an OR gate. Now these are generic, and again the internal structure of our half adder has an XOR and an AND gate. So these are generic way that the tool has elaborated my RTL code. So now the next thing is I need to define the constraint so that the delay that I want to measure from the input to the output is all being referred with respect to a clock. So the first task is to create a clock by providing the command create clock, and then I'm going to provide a period of 40 nanoseconds. So you don't need to specify any nano here. And the next comes the duty cycle, wherein here we are just trying to define from 0 to 20 nanosecond. We make the waveform high and then low. And then the next set of statement basically distinguish whether the clock is basically a virtual clock or the clock that I am taking from the design. So since the RTL code that I have is a combo, it doesn't have any clock signal, I'm just going to provide a virtual name clock. So this statement would actually create a virtual clock, and I'm just going to measure all the propagation delay with respect to this virtual clock. And next thing is we can define the clock skew using set clock latency, because as we know that the clock when it travels will take some amount of time, and there will be a skew when it travels through a longer distance. Since our design is of very small, I'm just going to give 0.01 nanosecond for the clock skew. So this actually sets some kind of reality into the design during my timing measurement. Now once this is done, the next thing is I need to define an input delay. So this input delay is nothing but I'm trying to define a delay a signal A, B and my Cin would receive the moment a clock appears across the input flop. Now in order to give this input delay, I need to know what is the clock to Q delay of the D flip-flop from my library. So in order to check what is the time, I'm just going to invoke and I'm just going to look into my clock to Q delays. Now here there are, for different transitions I have different timings, and the R stands for rise and F stands for fall. So the clock is rising in all the places because it's a positive edge triggered, whereas the other data is like Q where it is falling as well as rising depending on the data that I have. Now out of these I have a maximum value of 0.34 in the case of a minimum delay, and when I look towards the other end I have 0.49. So in order to have a margin, we will just provide time of 0.5 nanosecond, and we also will leave a margin for the propagation of the signal from the Q to the input pin like A, B and C, so which is nothing but the wire delay mod value, which we would take somewhere around 0.1. So basically I can right now define set input underscore delay, which is 0.6, where 0.6 is derived from clock to Q, which is 0.5, and 0.1 for the signal to propagate through the wire from the output of the flop to the input of my combo logic, either to A, B or scene. And then I'm going to define the clock. So this basically states that this delay is defined with respect to a clock edge or clock signal, and all the inputs are being referenced to this particular clock. So this actually sets the delay between my input A, B, C in has to have a 0.6 nanosecond from the output of the input flops. Similarly, I also need to set the output delay, where the output delay we have to account for the setup time and as well as the wire delay, which is the delay for the sum and the Cout to reach to my output flops. So we'll just go back again and look for the setup time. So here in this case, I have again a range of values, and for the case where I have the maximum value is 0.1, so which says that my data has to reach the D input before 0.1 nanosecond is what it has conveyed. So I'm just going to set that, and along with it, so I'm going to have that value plus the wire delay, which is around 0.1. So I have added both the setup time as well as the wire delay, which leads to 0.2, and I have to define these things to all of my outputs. So in this case, both my sum and carry. So click enter, and the next thing is to perform the synthesis process. Now, in order to perform the synthesis process, I need to provide the command synthesis to underscore mapped. So now when I invoke this particular command, the GUI which had OR gate and the inner half adders, which were basically built using XOR and AND gate, has to be replaced with the cells taken from our standard library. So now we'll just see this impact once I invoke this particular command. So now you could able to see that the OR gate is replaced with a NOR and an inverter, because these are the cells which are taken from the library that we have created, and even this XOR and even the AND gates were being realized basically from the inverter and the NAND and NOR. So our code has synthesized all of these things. Now the next thing is to generate the reports, for which I have to type the command report timing. So this command would actually give us the information about each delay that has incurred and the sleeve as well as everything. Okay, so we have a positive slack which is very high, which means that I can even provide a high frequency, which means that I can reduce the clock further down so that I can go up to a mark where 1000 picosecond is a nominal value. Here we have 38,000, which means that our clock period is so high and the data is processed within a fraction of the clock. But anyhow, this is just a demo point. I'm just leaving this to you to fine tune the clock and then step the time slack all the way down to 1000 picoseconds. The next thing is the area report. Since we have not provided any area information to the .lib file, we can skip that particular process. The final step that we have to perform is to generate the synthesized Verilog netlist file, for which we need to invoke the command write_htl with a switch mapped and a redirection operator and then the file name. So here I'm just going to give full adder underscore synthesis Verilog. So this actually writes the full adder which has been built using the cells that were taken from the standard library. So now we can just close this by invoking the command exit